Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to derive the means of several popular parametric distributions, and we're going to see that the mean value of these random variables is intimately connected to how we estimate their parameters from data. Let's get to it. So we want to study the mean of several parametric distributions. Those are going to be the Bernoulli, geometric, Poisson, exponential, and Gaussian distributions. So here I'm showing you the different parameters of these distributions. For the Gaussian, I'm only showing you the mean parameter. So we have a couple of videos on how to estimate the parameters of such distributions using maximum likelihood estimation. So you can go check them out. But basically, the maximum likelihood estimates for these parameters are equal to, in the case of Bernoulli, the sample mean or the average of the data. In the case of geometric, it's equal to 1 over the average or 1 over the sample mean. In the case of the Poisson, it's equal to the sample mean or the average. You can see where this is going. In the case of the exponential, is 1 over the sample mean or 1 over the average. And in the case of the Gaussian, the mean parameter is equal to the sample mean. Not the mean, well, the estimate for the mean parameter is equal to the sample mean or the average of the data. So we see that there's really like a very tight connection between how we estimate the parameters and averaging. In order to make this even more precise, we're going to derive the mean of the distributions in terms of the parameters. So in order to do that, we apply our formula for the mean of a discrete random variable, which is equal to a sum of all its possible values weighted by the corresponding PMF. Here, I recommend that you essentially try to do this for each of the distributions, and then you see how I do it, because that's how you're going to really learn how to do this, doing it by hand yourself. Okay, so for a Bernoulli, the Bernoulli has two possible values, 0 and 1. What's the probability of 0? 1 minus theta. What's the probability of 1? Theta. So the mean of a Bernoulli random variable with parameter theta is equal to theta. What about a geometric random variable? So remember that a geometric random variable represents how many coin flips you need until you get heads, when the probability of heads is equal to the parameter alpha of the geometry. That probability is given by alpha times 1 minus alpha to the k minus 1 for k coin flips, and we sum from 1 coin flip to infinity. And now in order to perform this sum, we're going to use an identity that comes from the geometric series. So here's the geometric series. You can look it up, but essentially the way it's obtained is by multiplying times 1 minus gamma and dividing by 1 minus gamma here, and then there's all of these cancellations. Now if we differentiate on both sides, we get this useful identity, which we're going to apply. So in our case, we almost have something like this, except that alpha is going to come out. And now we're going to set gamma equals to 1 minus alpha. So this sum is going to be equal to the alpha that comes out times 1 over 1 minus gamma squared, which is 1 over alpha squared. So at the end of the day, the mean of the geometric is going to be 1 over alpha. For a geometric with parameter 0.2, here the probability of heads is 0.2. How many times do we need to flip on average to get one head? 1 over 0.2, which is equal to 0.5. Here you can see the PMF. All right, what about a Poisson random variable? We again apply the formula. Now the formula looks kind of scary. Here what we're going to apply is the fact that the exponential of lambda can be expressed as this infinite sum. But in the Poisson, we don't have that exactly, because there's this k here. So what we're going to do is we're going to cancel k with k factorial. So we're going to get k minus 1 factorial here in the denominator. But now we're going to do a change of variables where basically we set k minus 1 equal to m. Notice, by the way, that because there's a k here, you could take this sum starting at 1, right? Because the first term is 0. So this here should start at 1. Okay, there's a little typo there. Again, these things is better if you just do them by hand and then you check. Anyway, so here, if we take out lambda, we end up with this sum of lambda to the m divided by m factorial. When we sum it, we're just going to get the exponential of lambda. So remember that there's this lambda that comes out. So that's why this survives, because this cancels out with the rest of the sum. So the mean of the parameter of a Poisson random variable no, not the mean of the parameter. What am I saying? The mean of a Poisson random variable is equal to its parameter. Here we have a PMF of a Poisson random variable with parameter a equal to 25. The mean is at 25. All right, so now let's take a look at a couple of continuous random variables. Here we're going to compute the mean by computing the integral of all the possible values weighted by the probability density. For the exponential, we plug in the exponential PDF, and now we integrate by parts. So, yeah, I mean, as usual, when we integrate by parts, we separate the function into a product of two parts. One we differentiate it, the other we don't. Here, I guess it's just easier if you just do it by hand. What I will say is that this term here is equal to 0 because you have an a here and an infinity there. Okay, so it's equal at 0 and at infinity, so this is going to cancel out. And now we have this integral. What is this integral here? This has to integrate to 1 because it's an we're integrating the PDF over the range where it's non-zero. To be a valid PDF, it has to integrate to 1. So we end up with this result where the mean of the exponential random variable is 1 divided by its parameter. If we plot this, this is the PDF that is non-zero from 0 to infinity, and the mean is at 1 divided by the parameter. We have arrived at our final random variable, which is the Gaussian. Again, we apply the formula, we plug this in. This might look a bit scary, but we can take a change of variables where t is equal to a minus the mean parameter divided by the standard deviation parameter. And when we do that, we get this expression, where this is an odd function where the integral is going to cancel out. You're going to get like plus the same quantity on one side and minus on the other when you integrate from minus infinity to 0 and then from 0 to infinity. So this is going to be 0. And here we have mu that comes out and an integral of the PDF from minus infinity to infinity, which is going to be equal to 1. Again, I just recommend that you do this by hand. And we have that the mean of a Gaussian random variable is equal to its mean parameter, which is, thank goodness, because we call this thing the mean parameter for a reason. All right, so this is where remember that a Gaussian is centered at its mean parameter. That also happens to be its mean and its median. This doesn't happen for other random variables. So remember that the way we estimate the mean of a random variable is by taking an average, an arithmetic average, which is the sample mean. This is not a coincidence because we define the mean so that it approximates this average when we have many, many samples. So it's not a surprise. Now, let's express the maximum likelihood estimator in terms of the sample mean and compare it to the function of the mean as a function of the parameters of the distribution. So for the Bernoulli, the maximum likelihood estimator is just the sample mean, and the parameter is equal, the mean is equal to the parameter. So we could have estimated the parameter by saying, well, the parameter is equal to the mean. So how about I look at my data, I approximate the mean, and then I set the parameter equal to that. That would have given us, that would be equivalent to the maximum likelihood estimator, but it's a different way of arriving at that estimator because we have not considered likelihoods at all. That is called the method of moments. We will see that for all of this distribution, the method of moments give us exactly the same estimate of the parameter as maximum likelihood, but that is not the case for other distributions. So here, the geometric, we have that the maximum likelihood estimator is 1 over the sample mean. Not surprisingly, the mean of the random variable in terms of the parameter is 1 over the parameter. So this, again, is equivalent to saying, oh, the mean is 1 over alpha. What is the sample mean of the data? I'm going to basically use that to plug in the expression for the mean as a function of. That was really complicated. So what I'm saying here is that if you want to set alpha now so that these guys correspond, then you set alpha equal to 1 over the sample mean, which is exactly equal to the maximum likelihood estimator. That's called, again, the method of moments. For the Poisson, same thing. The maximum likelihood estimator is the sample mean. The mean of the Poisson as a function of the parameters is lambda, right? So if you want to estimate lambda from the data, you can just set lambda equal to the sample mean. Again, method of moments, which is in this case equivalent to maximum likelihood. Same for the exponential, we have 1 over the sample mean. The mean is equal to 1 over the parameter. Same for the Gaussian, sample mean. So if we want to estimate the mean of a Gaussian, it's kind of natural to set the parameter equal to the sample mean, and that's equivalent to maximum likelihood estimation. All right, so hopefully this clarifies even further the connection between the mean and averaging and the parameters of these parametric distributions. And also it introduces you to an alternative way of fitting parametric distributions, which is trying to fit the mean of the distribution using the data, approximating the mean with a sample mean. And that's all I got. We have learned the mean of different parametric distributions, and we have also learned about the method of moments, which is an alternative way to fit parametric distributions, which often gives us the same result as maximum likelihood, at least for these popular parametric distributions, but that's not necessarily the case. In other distributions, it could give you a different result. And that's all I got. Thank you very much.